conventional or traditional techniques of homology by which we find out these Betti numbers, that is an invariant associated with a topological space, and what is the problem there, and how to get rid of those problems. The problems identified in the conventional types will be tackled using a particular newly introduced type of homology called persistent homology, and that we will introduce, and how through some filtrations. That filtration means when you vary a particular type of parameter, when what will be how that the shape of the space will be changing over that parameter values, and what is will identify what is a persistent shape or what is persistent nature that is associated with the space, and that will be regarded as a signal. The other ones, that is those shapes or those patterns which came and vanish for a very short time, can be neglected without any problem, and that will be regarded as noise. The other one will be regarded as the signal. And this birth and death will be the point where these signals or point where these patterns starts appearing, and the death is the point where they disappear. And you find out over what duration or what range of the filtration parameter these values are persistent, and those will be considered as, therefore that will be represented using a barcode. You may be familiar with the barcode reader and other things, and this concept will be represented using some barcodes, and that will be the brief outline of my that is the brief outline of my talk. Now coming to the basic things, algebraic topology, this is one of the recent branches. And in fact, this is concerned with the identification, description, and discrimination of high dimensional objects. Therefore, in contrast to the more geometrically inclined field of the differential topology, the algebraic topology methods rely solely on the connectivity of a space. That is what I told you. The major tool that we'll be making use here will be the connectivity of the space. Is the connectivity of the space, and now we need by reasonable computational means, but also discriminative in the sense that it should only us to distinguish from one form of data to from other forms of data. That means when you do go for such a computation, it should be computationally feasible. It should be computationally feasible as well as it should be computationally feasible as well as we should be clearly distinguish one form of data from other form of the data. These are the two, in fact, often contradicting things that we need to achieve. Therefore, there should be a give and take between these two. Therefore, we want to understand higher dimensional objects, as I mentioned, where human intuition fails beyond dimension 4. And topological approach is that by identifying some intrinsic properties of high dimensional spaces that do not change under some transformations. Now we know there are transformations which do not change. There are some things that do not change under transformations, under some transformation, and these properties we referred as invariants. Invariants, in fact, a reasonable transformation that may be ignored is a set of affine transformations such as movements and rotation. Therefore, these transformations, when I move from one space to other space, there will not be any change in my shape, and then I move from one space to other space. If I rotate, there will not be any change in my shape, my shape. Therefore, these can be they are of not much importance when we consider with the shape of the data. Therefore, that can be ignored. And even algebraic topology, we even ignore a larger class of operations, and that will be called that can be ignored using in fact that will be called operations which are called described by operations which are described by homeomorphisms. Therefore, when we say that whenever we have one space is homeomorphic to other space, there are no need of considering them separately. Their properties will be considered together. Now, this is a definition of a homeomorphism. that you are all know. It's a function from a space X to Y. X and Y are topological spaces, and should be bijective, continuous, and its inverse also should be continuous. Now these are some examples. A cube can be deformed into a sphere. Therefore, these two can be considered as homeomorphic. But both objects are non-homeomorphic to torus because it is impossible to obtain a whole of the torus without cutting the sphere. There are some operations which are permissible and some operations which are non-permissible under this type of transformations. In fact, you can shrinking, stretching, etc. things are possible, but cutting, gluing together, etc. are not possible. Therefore, we can get one from other under this allowable transformation. Then we say they are homeomorphic. In other words, a homeomorphism is any transformation that involves stretching, translation, and bending, but neither cutting nor gluing. The characteristic properties of a space must not change under these type of transformations. And sometimes, in fact, this type of transformations may seem to be weak. That means this type of classifications via or up to homeomorphism seems sometimes weak. That means that will not serve our purpose. Therefore, what we need is a much more higher discriminative power. Therefore, whenever, even though we want to distinguish between two homeomorphic images, then the homeomorphism type of transformation will not work. This type of invariance will not work. If you need in many of these data analysis techniques, we need something more than this. Therefore, this is not enough for us. Therefore, there is a tool that is called a persistent homology that to detect more variation in data sets. That is what is persistent homology. And this is the summary. Homology is an algebraic method for discerning topological feature of data. And persistent homology is a well-developed tool which allows topological analysis of large data sets. From a topological perspective, now what we input here is a filtered complex. So we will come to see what is later we will see what is a simplex, what is a complex, and from that how we will find out or construct a topological space out of that. All these things will be. Then a filtered complex will be input. That means a filtered complex will be obtained, as I mentioned, while we vary the filtration parameter, the shapes of the data will be changing, and with reference to each value of the filtration parameter, we will get each shape. That will be called each one will be called a filtered complex. Therefore, that filtered complex will be input, and output will be a sequence of collection of intervals, one for each dimension, called a persistent barcode. Our output will be a barcode that, as I mentioned, that we even don't know from which dimension the data comes. Therefore, there will be a barcode associated with each dimension. If data is coming from dimension this is the barcode. If data is coming from another dimension, this is the barcode. Now, corresponding to every dimension 1, 2, 3, there will be a barcode, and that will be the output. The barcode gives information about homology class, which are born and die as you vary the scale. That is a filtration parameter. And this is what is the very brief and non-expert summary of today's talk I am going to give. Therefore, this is what we are doing. Now, what we do is that we start with a set of points. On the left side of the screen, you can see that there is on the left side of the screen, you can see that there is a set of points. It may be coming from some arbitrary space, maybe Rn or whatever it is. A neighborhood relation permits us to query any point about its connectivity. Now, what we precisely want to do is that given a set of points, given a point cloud, first of all I will construct a topological space out of that. How to impose a topology on these points? How to construct a topological space out of that? And after constructing the topological space, I will vary the particular parameter which I used for constructing the topological space, and I will get a filtered complex of, in fact, they are nothing but a collection of topological spaces, and we will study the nature associated with that. The right part shows one particular topological space of points Now, if I have an edge between these 2 points, that precisely means that there is a relation between those two, or the one is a neighbor of the other. Therefore, through this neighborhood relation only we can construct a topological space. Therefore, but it is not always necessary that they correspond to our sense of proximity. An edge near to one edge may not be a neighbor of that, but maybe a distant edge can be a neighbor. That means physical proximity can be considered as one of the parameters, but not necessarily always. For example, my friend may be in US and there will be an edge between me and US, and somebody sitting next to me may not be a friend of me and physically close, even though I may not have any connection with them. That is possible. That depends upon the situation. Now, how to distinguish between these shapes? Therefore, very simply, simple topological invariant, for example, is given by the dimension of the space. But it is not a great matter. Therefore, Rn and Rm we can distinguish when m not equal to n. In real world data, we don't even know what is the correct dimension of the data. Therefore, it is quite impossible or quite difficult to use such a distance. It's not of much use. Now, what we need is a more balanced invariant, and the motivation for symbolical homology is to use the number of holes in a topological space as the invariant. You find out how many holes are there in a topological space, and you use that as an invariant. And for identifying this, we use the notion of connectivity. For this, we require the topological space being described by a simplicial complex. That is one of the basic building blocks in algebraic topology. A simplicial complex is a data structure that explains how to glue together a topological space from poles. As I mentioned earlier, my first aim is to construct a topological space out of given set of points. That will be done through using these simplicial complexes. We construct these simplicial complexes, and these simplicial complexes are nothing but edges, triangles, tetrahedra, and their higher dimensional generalizations. Simplicial complexes are thus serve as the blueprints of a space. The points, edges, and other entities that make up a simplicial complex are known as simplicious. So this is the definition of a simplicial complex. Simplicial complex, given a family of sets, any subset of cardinality k+1 is called a k-simplex. Now, this is a general algebraic definition. When you talk about in graph theoretic terms, we may think of 0 simplices as vertices, 1 simplices as edges, and 2 simplices are triangular faces. Therefore, obviously, this can be triangular faces means a triangle, where filled triangle with the triangle with the three sides and the region in between them, filled triangle. In fact, 0 dimension they are vertices, 1 dimension they are edges, 2 dimension they are filled triangles, and 3 dimension the analogous is the tetrahedron, and those will be considered as simplicial complexes. Now, this is the definition of an abstract symbolical complex. A simplex we have defined. Now, the union of the simplexes will give you a complex. That is how we are getting symbolical complex. A family of K with a collection of subsets L is called an abstract symbolical complex if singletons V belongs to L for all V belongs to K. This ensures that the set of the singletons are formed the part of the complex. That means they are called the vertices or the vertex set of K. And if sigma belongs to L and tau is a subset of sigma, then tau will also belong to L. And tau is referred as a face of sigma, and sigma is referred as a co-face of tau. Now, there are 2 conditions to be satisfied by a symbolical complex. The importance of these 2 conditions is that intuitively the first constraint is required to ensure that the symbolical complex contains all 0 simplexes. the simplicial complex contains all zero simplicious, that is, it contains all vertices. The second one ensures that the subsets, that is the simplicious, only intersect along shared boundaries. That means they cannot intersect as they wish. It can be they can intersect only along shared boundaries, as you can see in the figure. Now the left side is an allowable valid simplicial complex, and the right side is an invalid one. And the left side, you can see that they are intersect along a face only, either through a point or they are intersecting through an edge here. But here you can see that non-face intersections are here. Therefore, these things are not possible. These types of intersections are not possible. If you want to construct a complex out of the simplicious, obviously this is the way to construct it, and this is not the in homeomorphisms also there are some allowable operations are there and some non-allowable operations are there. Just like that, here also some allowable gluing together of simplexes are possible, and some invalid ones are also there. These are the possible ones. Now a face or skeleton, what is meaning? Given a simplicial complex K, the set of all simplicious with the dimension less than or equal to K form a valid simplicial subcomplex. This subcomplex is called a K skeleton of K, called a small k skeleton of K. If the dimension less than or equal to small k will form a K skeleton of the complex. Thus, one skeleton of a simplicial complex only contains zero simplicious and one simplicious. That means one skeleton is always going to be a graph. And how these things will work, obviously it is guaranteed by a major theorem in algebraic topology that is called the Symbolical approximation theorem. And in fact, this is not only valid for complexes, it is valid for any combinatorial triangulation. That is, in fact, in the sense of a smooth manifold. Therefore, such kind of approximations of a space by a simplicial complex is guaranteed by a theorem called the Symbolical approximation theorem that is stated here. And without giving definitions of all the terms, I'll just state that every smooth manifold admits one essentially unique compatible piecewise linear structure that is equivalent to a combinatorial triangulation. That is what is called a simplicial complex. Therefore, this theorem guarantees that such an approximation is valid. Therefore, that all constructions are based on the validity of the construction that we are going to see is based on this major theorem in algebraic topology. Anyway, now from the perspective of computer science, this is very important, at least for two reasons. The one is that there are numerous smart data structures available for storing a simplicial complex efficiently. Therefore, simplicial complexes can be stored efficiently using some smart data structures. The calculation of simplicial homology or simplicial complexes boils down to matrix calculation. While we calculate for simplicial complexes or homology, when we go for the homology group of the simplicial complexes, obviously this can be done with a very simple calculation consisting of matrices only, the row column operations in matrices, some decomposition, etc. will work it down. Therefore, the calculations can be done smoothly in computers. These are two important things in the perspective of computer scientists. Therefore, what you do is that we will find out boundaries. Therefore, what I told you that we are doing it via connectivity. Via connectivity means we will identify the number of holes, and holes are those portions in the space without any boundary. Therefore, first of all, we need to find out boundary or calculate boundaries of a simplicial complex. Then we look for those parts of a simplicial complex that do not have a boundary. That will be a hole. This idea requires the definition of a boundary operator for a simplicial complex as well as a formal structure A boundary operator may be needed. Therefore, if I have a symbolical complex, you apply that operator on the symbolical complex, you get a boundary. Naturally, in dimension theory, we know that when we take the boundary of a space of dimension 3, then obviously the boundary will be of dimension 2. That a boundary operator will reduce the dimension of a space by 1. So here we need a boundary operator. As far as a formal structure we will introduce, as an algebraic structure we will introduce, and that will be called a chain group. In chain group, there will be some elements. We'll see what are the elements in the group, and we'll see what are the operations in the group. Then only it will be my construction of the group will be complete. I will construct a chain group for that. And for the entries for the members of the chain group, obviously that will be chains. We'll see what are chains, and for that chain we will introduce the boundary operator. In fact, we will see that boundary operator will be a homomorphism with respect to the group that we are introducing, the chain groups. In fact, the boundary operator will be a chain group. In fact, boundary operator will be a homomorphism from chain group P to chain group P minus 1 as the boundary reduces the dimension of the space. Therefore, this is the formal algebraic structure that we are going to define on a symbolical complex. This is a definition. Given a symbolical complex K, we will define the pth chain group. I told you already that all our discussions will be done for various dimensions separately. Therefore, we need to do everything for each dimension separately, and P is our dimension. Given a K, complex K, we'll find out the chain group Cp for K. And this is defined by all formal linear combinations. That means the members of the group are formal sums of simplicious, P simplicious in the complex, and they will be of the form sigma I, sigma j, that the summation over j sigma j will be that, where each sigma j belongs to the complex K. And that means the coefficients will be either 0 or 1. Either 0 or 1 means in a complex, a coefficient of a simplex is 0 means in that complex that simplex is not at all present, and if it is 1 means it is present there. That means it is a part of the linear combination or not. The restricting coefficient to 0, 1 has many advantages. That means we can do under addition modulo group 2 Z2, you can work it down, no problem, since 0 and 1 only are there. That's 1 plus 1 is 0. And that is the operation that we are going. That we can see that this particular type of modular 2 addition is similar to when we transform them to set theoretic terms. In fact, that will be similar to the symmetric difference. Therefore, the symmetric difference of the operations can be achieved by doing these coefficients, taking 0 and 1, doing addition in modulo 2. And the elements of the pth chain group is called CP are called simplicial chains, and each simplicial chain is thus a linear combination of p simplices. The chain group is an abelian group. Once we construct such a group, we can identify that this group is going to be a abelian group, and operation given by the symmetrical difference between symbolical chains. Therefore, actually the symmetrical difference A of A and B are that means A union B minus A intersection B, that we just remove whatever is common there. Therefore, if you add up two chains like that, if the coefficients of two simplexes are 1, obviously it will be adding up 1 plus 1, 2, 2 is 0. That means that chain will be removed. That is, whenever it is common, that part is common, that will be removed. That is how we are obtained is similar. What we say that is similar to symmetrical difference between simplicial chains. The operation of strings or linear combinations under modulo 2 is similar to symmetrical difference between symmetrical chains. Both are same. We are now able to define, in fact, we have defined a chain group, and now we define the boundary. In fact, we see that we can prove that this boundary is going to be a homomorphism. The boundary will be defined as, given a symbolical complex K, the pth boundary homomorphism is the map that assigns to each simplex, it will assign its boundary. Now, the boundary is given by, if you have a simplex with the vertices V0, etc., Vp, then its boundary is given by delta P sigma that is a summation of V1, V2, the simplicious V1, V2, Vi cap, Vk. That means Vi cap stands that particular vertex is not present in that particular entry. That means in summation means in the summation the first term V1 will be absent, and in the second term V2 will be absent, etc. In the ith term Vi will be absent. Therefore, you are going to have a dimension 1 less when you apply the boundary operator delta. In fact, P should also be there. Each one will be for each dimension. One dimension, this P will be there also. Therefore, we can define dou P from Cp to Cp minus 1, and we can verify that it is a homomorphism between chain groups. This is an example. Now, if you have here we have a triangle. The boundary of the triangle is non-zero, where now in 2 dimension we have the filled triangle ABC is there. When you apply dou 2 for ABC, in the first stage what we are having is that A will be absent. We have a summation where A will be absent. When A is absent, it is edge BC. In the second case, B will be absent, then edge AC will get, then edge BC, AB. Similarly, C will be absent. Therefore, dou 2, therefore the boundary operator applied to this filled triangle will be equal to the union of these 3 edges that you will be getting. And these edges, on the other hand, do not have a boundary. That is, again, if you go for this, the boundary of these edges, that is, these are in 1 dimension. Therefore, delta or dou 1 of these 3 will be, dou 1 of BC will be, we just remove B, you'll get C. Just remove C, you'll get B. That is C, singleton C plus B plus C plus A plus B plus A. Therefore, each one occurs twice. So that when you add up that, obviously the coefficient becomes 2. 2 is equivalent to 0 under modulo 2. And it's at 2. We are all doing the operation. Therefore, what do you get? 0. Therefore, the boundary do not have a boundary. Boundaries itself do not have a boundary. That is, when you apply the boundary operator twice, obviously what you are ending up with the 0 only. We are ending up with the 0, or the NT group will be ending up. Therefore, boundary applied twice will always give you 0. Once you have a boundary operator defined, it is shown that dou P minus 1 composed dou P is always 0, and you can connect them through this boundary operator connects the chain groups. In fact, using this homomorphisms, which are nothing but boundary operators, will connect it. Therefore, now we come to this homology group. The construction begins with, in fact, what I am going to do is that we are going to construct, we are going to find out the number of holes in the topology. The construction begins with a chain group. Therefore, whenever you have a point, now what we have done so far is that we have a chain structure. In fact, we have a point cloud. We have a point cloud, and from the point cloud, using some neighborhood relation. Now later we will see how that neighborhood relation can be established via some parameter. Through that, we will construct a topological space using the concepts called by constructing simplicious, and by gluing together, patching up that simplicious, we will get a complex, and that complex, as the Symbolical approximation theorem says that there is a one-one correspondence between a topological space and its Symbolical complex associated with that. That means that will correspond to, uniquely correspond to a topological space. That is space we have constructed that. And the linear combination of the spaces, the linear combination of the simplices inside a complex or the space will give you a chain group. And the construction of the chain group, the construction begins with a chain group Cp, whose elements are nothing but P chains, which for a given complex are formal sums of P-dimensional cells that we have also already seen. And the boundary operator is from Cp to the Pth chain group to the P minus 1 to chain group, that we see how that boundary operator applies. In fact, writing the groups and mappings in sequence, we get the chain complex. The chain complex is like you write down all the groups CP, CP minus 1, CP plus 1, etc. and connect them through the boundary operator. Connect them through the boundary operator, which is nothing but a homomorphism defined on that. That is, dou P plus 2 will be applied on CP plus 2, and it will be, and the value will be given in CP plus 1, and dou P plus 1 will apply on CP plus 1, and entry will be in CP. That means you can always find out, you can always find out what is the image of a boundary operator. The image of a boundary operator, in fact, image of a boundary operator, it will be obviously that will be a boundary of a complex. And obviously we can think about dou being a homomorphism, you can think about the kernel of that particular homomorphism. Kernel of a homomorphism, you know that all those elements which are mapped to identity on the right side. Therefore, you can think about them. We can think about the kernel. The kernel and the images of the boundary homomorphism. That are the two important things we are going to concentrate, and using which we can define the homology group. The kernel and images of the boundary homomorphism are the cycle and the boundary groups. Now you already know that the image is going to be a boundary, and the image is going to be a boundary, and the kernel is those elements which are mapped to 0. Therefore, kernel means boundary is 0. Boundary is 0 only for a cycle. Boundary is 0. You already seen that for a triangle, non-filled triangle, that means a cycle. For that, the boundary is 0. That we already seen. Therefore, all those who are mapped to, all those who are mapped to identity on the right side. Identity is the 0 simplex on the right side, will be nothing but cycles. Therefore, we will see them. Therefore, for every P, boundaries form a subgroup of the cycle, and we take. Therefore, these two are, in fact, images and the boundaries form a subgroup under the same operation that we define. Therefore, whenever cycles form a subgroup, we can go for the quotient group, which gives a group whose elements are the quotient groups. We know the elements of the quotient group are equivalence classes. In fact, here they are called homologous cycles. In fact, the members are cycles. That means one cycle, and all in one cycle there will be other cycles which are homologous to that. All those will form an equivalence class there. This is the pth homology group, denoted as HP, where P is again the dimension. That means what we are doing is that we have a using the boundary operator, we have, which is a homomorphism, we have the kernel and image, and you take the quotient of that, that is kernel of dou P2, image of dou P plus 1, kernel of dou P2, image of dou P plus 1, and that will be defined, that quotient group will be defined as the homology group of order P. The pth homology group is nothing but the quotient of these two. Now, there are so many things associated with the quotient group, and in fact, so many operations can be defined. And as I mentioned, that the homology classes will be there. They are equivalence classes, or 𝑰𝒏𝒕𝒓𝒔𝒕𝒊𝒐𝒏 equivalence classes will be nothing but homologous cycles here. And it has a rich structure, and we are not interested in that structure, but we are interested only in a short summary given by Betti numbers. A short summary of this group is given by Betti number. In fact, Betti number of homology group HP is nothing but the algebraic rank of that pth homology group. The algebraic rank of the homology group is defined as the Betti number associated with the HP. Therefore, what do you mean by algebraic rank? Algebraic rank is the cardinality of the smallest subset which can generate that group. That is by definition the rank of algebraic rank of a group. Therefore, you find out the algebraic rank, the cardinality of the smallest subset which can generate that particular group, that will be considered as the Betti number. And in fact, that's the definition of the Betti numbers. Therefore, this Betti numbers actually counts the number of holes in each dimension. Therefore, that is the significance of this Betti number. Betti numbers are commonly used to distinguish different topological spaces from one another. This even work regardless of their dimensionality. For example, if you have something like this, now this is a topological invariant. Betti numbers count the number of holes in different dimension that occur in an object. Therefore, in 0 dimension, these Betti numbers count the connected components. In 1 dimension, they count tunnels, and in again beta 2 counts the voids there. Beta 0 connected components, beta 1 tunnels, beta 2 voids, etc. For example, some examples I have given. I have a point, a circle, sphere, torus, etc. are there. For all these ones, we can calculate if you calculate the Betti numbers, and if the space is a point or a circle or a sphere or a torus, you can see that the beta naught value, the connected components always is 1, 1, 1, 1 we are getting. And beta when the tunnels 0 here, in a circle it is 1, and for a sphere it is 0, and for a torus there are 2. And voids, point 0, circle 0, sphere there is 1 void, and for torus there are 2 voids are there. Sorry, only one void here inside this one. Therefore, that is the Betti numbers. This Betti numbers gives the number of holes in different dimensions. For each dimension, we will getting one Betti number, beta 1, beta 2, beta 3, etc. Now, as I mentioned that there are some problems associated with the Betti number. This Betti numbers counts the number of holes. It will not distinguish between what is a significant shape of the significant hole and which one can be eliminated without any problem. That means when we vary the parameter epsilon, that is the filtration parameter, as I mentioned that there will be a series of simplicial complexes that we'll be getting, and there will be some shapes, some holes or voids coming and vanishing. But Betti number will not consider that. For if you count the Betti number, the small ones, insignificant ones cannot be ignored. The standard topological construct of topology of homology offer no such slack in their strident rigidity. A hole is a hole no matter how fragile or fine it is. Therefore, that is the problem with associated with it. That is a problem associated with while doing with this Betti numbers. Therefore, what we need is we need a more flexible one. That is what is given in a persistent homology. Persistence introduced by Edelsbrenner, Letzter, Samarodian, Carlson and Samarodian, etc. is a rigorous response to this problem. That I mentioned, the Betti numbers are not sufficient. That means given a parameterized family of spaces, those topological features which persist over a significant parameter range are to be considered as signal with the short-lived features, and the short-lived features as noise, as I mentioned, which persist over a significant parameter range will be considered as signal, and those who are short-lived will be ignored. Those who are short-lived will be ignored as a noise. That is the significance of this. Now, these are some more definition that we'll be using. We are familiar with what is a digital image, and point clouds I already mentioned. The set of points that can be finite but very large in number, for which we are constructing a topology. Subset of ambient space that satisfy regularity conditions of one kind or other. The some regularity condition, some points, some subset of the point cloud satisfying some regularity condition is called a shape. Therefore, we want to identify hidden shapes or hidden patterns or hidden structure that is in the data. I told you that how to construct a topological space out of that. That is mentioned that it is mentioned that given set of points, I want to construct a simplex out of that, and using simplexes, you can go for complex. Therefore, there are two ways of constructing a complex. The first one is called a check complex, and second one will be called a rip complex. Given a point set X in a metric space and a number D greater than 0, there is some value D. The check complex is the symbolical complex whose symbolisms are formed as follows. How you define a check complex? How you construct a check complex from a point cloud? For each subset S of the point X, form a d/2 ball around each point and include as a simplex of dimension equal to the cardinality of S. If there is common point contained in all of the balls in S, this structure obviously satisfies the definition of the symbolical complex, and any subset of the simplex will also be a simplex. This is how we are constructing a complex. Therefore, what you do is that you construct balls of radius d/2 around each of the points. And if there is a common point constraint in all of the balls, therefore, if you take a subset, if you collection of sets, say if there is a for all those neighborhood, if there is some intersection point is there, obviously using all those balls, you construct a complex of dimension which is equal to the cardinality of the set S we are defined, if the intersection is non-empty. In a similar manner, you define the Ripf complex. In the check complex, we are constructing the complex if the intersection is non-empty. In a Ripf complex is similar. Only thing is that we construct a complex only if they are pairwise. They have pairwise intersection. They are intersecting pairwise. Therefore, in the earlier case, if you have 5 points, there should be something common for the neighborhood of each of the 5 points. Then you can construct. But here it is not necessary. If they are pairwise intersecting, then also you can construct it. This is the example. Now this is how we construct neighborhoods about each of the 3 points. And here you can see that there is no common point of intersection. So that if you go for the construction of a check complex, we cannot connect them. We cannot connect them because they have no common intersection. Therefore, they will stand as points itself in the complex also. But if you go for the Ripf complex, since they are pairwise disjoint, you can connect them. Therefore, since these two are intersection of these two are non-empty, there will be edge like this one. Therefore, you will get a non-filled triangle. You will be getting. In fact, you will get a filled triangle. You will be getting, since all these 3 has non-empty intersection. A filled triangle will be getting. Now, this is what you are getting. Now, if you have a point cloud here, you have a point cloud here, you have a point cloud here, then you are constructing balls of radius d/2 about each of the point that I have constructed. And if you use the first rule, the check rule is that I can connect only if they all intersect. And if you use the Ripf rule, then I can connect their pair. If you take these 3 points, 1, 2, 3 points are there, you can see that they have nothing in common, no common intersection. But these two intersect, these two intersect, these two intersect. Therefore, I have edge like this, and this in check complex. But in Ripf complex, the definition is that if all these three are pairwise intersecting, obviously you can connect all the 3. And you can fill the triangle also. Therefore, it will be a filled triangle because this will be a 2 simplex. Here only we have 3 1 simplexes only are coming. Here you have a 2 simplex, since the definition is different. Therefore, if you construct the check complex or the Ripf complex, some slight changes will be given there. And based on your requirement, you use either check complex or the Ripf complex for the construction of the topological spaces out of the given point cloud. Now, this is the theoretical development, how these things can be carried out theoretically, how the arguments are valid. Now, we have a real valued function f from T to R. T topological space R is a set of real numbers. Then the sublevel set for each A is defined as T suffix A equal to inverse image of minus infinity A under F. Inverse image of minus infinity A under F will be called the sublevel set, and we can see that the sublevel set preserves the order. That means if A is less than or equal to B, TA is going to be a subset of TB. And this inclusion includes a map. Whenever we have an inclusion here, obviously, if whenever we have an inclusion like TA subset of TB, we can define the inclusion map in the homology groups. In fact, if I is the inclusion of TA to TB defined as X going to X itself. Since TA is subset of TB, any element here can be mapped to the same element here, since TA is a subset of TB. Therefore, that is defined by this particular map X going to X. And in algebraic topology, the inclusion maps with reference to the homology groups are always denoted by putting a suffix star. When I have an inclusion, the inclusion map in the homology group will be defined by I star. That is, I star is the inclusion map on the homology groups of TA and TB. That is 𝒏𝒕 to 𝒏𝒕b. For simplicity, you will denote it by F. Rather than putting I star, I denote it by F. Now we have a sequence A1, A2, etc. We have an increasing sequence like this, corresponding to which we have a sequence of homomorphism induced by inclusions. Therefore, corresponding to this sequence, we will be having a sequence. Since A1, A2, here A less than B, that means we have a TA1 to 𝒏𝒕 to 𝒏𝒕b. Similarly, A1, A2, etc. A now here you have homomorphisms like this. In fact, you have mappings anyway. When coming to that, you have mappings like, in fact, a trivial group to 𝒏𝒕, homology group 𝒏𝒕1, then going to 𝒏𝒕2, etc. Now you can see that if this inclusion satisfies the transitive property, because whenever you have a TA1 subset of TA2 subset of TA3 implies that TA1 is a subset of TA3 also. Therefore, the problem is that the thing is that from rather than going through this one, you can jump from an ith stage to a jth stage here. Since TAI is a subset of TAN, therefore directly you can jump. Therefore, that will be denoted by, in the direct going is denoted by F, and then F of Ig will be represent that particular jump from the ith stage to jth stage. That is, Fijp will be a mapping from 𝒏𝒕i TAI to 𝒏𝒕aj. So from AI to AJ, I can have a jump like this, and the P takes the value. In fact, P takes the value between 1 and n1 into this dimension. The homomorphism for each dimension will get to 1 Fij will be there. This is a homomorphism. The homomorphism Fij takes the homology classes. In fact, you can say these are the homology group of TAA. Therefore, the elements here are homologous cycles or homology classes. That are the classes of the equivalence relation. And that will take the homology classes of the sublevel set TAI to that of sublevel set of TAI AJ. That will be done. Therefore, this Fij will be a homomorphism from the homology, the pth homology group of TAI to the pth homology group of TAJ. Now, the image of this homomorphism, you can find an image of Fpij for ij between 1 and n, integer values between 1 and n. The pth persistent homology group is defined as the image of this Fpij. Therefore, the pth persistent Betti number you can define as the rank of this Hpij. Therefore, the pth persistent homology group is defined as the image of Fpij, and the rank of Hpij is defined as the pth Betti number, that will be denoted as beta Pij. Therefore, analogously to Betti number and analogous to homology groups, we define the persistent homology group and persistent Betti numbers, which has a much higher discriminating power than the conventional classical Betti number, which gives the rank of the homology group. Here it is the rank of the persistent homology group. This is what I told you, that this is how that the sequence of filtrations are coming. I told you that when you vary the filtration parameter, you will get different types of Symbolical complexes K1, K2, etc. That will serve as the homology groups. In the earlier mapping we have seen, the sequence we have seen homology groups. Here actually these homology groups will be nothing but these complexes, Symbolical complexes given like this. Consider a Symbolical complex K and a function f from K to R1. We require that the function f is monotonic, which means it satisfies the property for sigma j subsets of j, f of sigma j will be less than or equal to f of j. That is one of the fundamental requirements that we have seen earlier also. This is the requirement. TA should be subset of TB. That is needed here also. What we need is here. f of sigma j is less than or equal to f of sigma. That is for all sigma j subset of sigma. Therefore, this order should be preserved. That is, it is a monotonic. This mapping should be monotonic. And this property ensures that the sublevel sets that we defined, my inverse image of minus infinity a under this one is going to be, I think I am audible. My connection has no problem till now. Okay. Now, denoting these simplexes like this K1, K2, K3, etc., this property ensures that the sublevel sets are subcomplexes of K for every alpha belongs to R, denoting Ki equal to F inverse minus infinity Aj, Ai. We get a nested sequence of subcomplexes of K, which is called a filtration. Therefore, we have a filtration like this. And naturally, by definition, we have the pth persistent homology group is there. This is a notation, and we can think about that. Therefore, when we start from, we have a sequence of homomorphisms, as I mentioned earlier, and the pth persistent homology group consists of all those classes. I told you that we have a jump from the ith stage to jth stage. And those homology groups, persistent homology group, consists of all those classes which survive from the ith stage to jth stage. Now, this is what is we are saving. That is that when we have a class is born, then it is called a birth. When a class merges with an already existing class, it is called a death. And this is mathematically what is a birth and death, and that will be more clear. This will be more clear when you go for some example. Therefore, this is the persistent modules. In fact, in general, that can be written as the sum of the, we can represent it using a direct sum of vector spaces, and that also in a more general way. Anyway, the direct sum of the vector spaces and linear maps in more general way it can be done. Anyway, we are not going to that much details now. Now I'll come with some example. And this is how, in fact, in the left side, you can see, I think my time is running out. It is almost 11:50, 45 now. Anyway, on the left side, we have a sequence of points are given here. And from these points, how I will construct a barcode? That is my question. Therefore, is there any, in fact, you can see that, is there any hole there? You can see that there are some B here, but there is no hole. There are no filled holes there, but still. Now here we have the value of the filtration parameter is 0. That is the value of the neighborhood. The diameter, the value of the diameter is 0 here. There is nothing is coming here. And when you increase the value of the, obviously, I have increased the value of D. I have increased the value of D. Here also you can see that there is no holes coming here. There is no holes coming here. The value is increased to maybe some 4 units or something. If I again increase, now you can see that there are some holes have come there. There are 1, 2, 3, 4. You can count the hole. Therefore, whenever a hole is starting, I start drawing a bar, and I will draw that bar till that hole ends. That's the significance of this barcode, and this is the particular value of epsilon, the diameter value. Corresponding to this diameter value, you count this line cuts at how many bars. The number of bars cut at each point will give you the number of holes associated with that particular value of epsilon. And again, if I increase, if I increase, now you can see that again the number of holes, some holes has disappeared. This is stopped here, and some new ones have started. Now you can see that 1, 2, 3, 4, 5 holes are there. 1, 2, 3, 4, 5, 6 are there. One is just ended here. Obviously, therefore that will give you. Therefore, these are the holes. Now you can see that there are some holes which are persisting, some holes are which are vanishing. Again, now finally you have one hole. Again, I increase the diameter. Again, one hole only. That means there is a hole starting from here to here. Now you can see that throughout this entire one, this particular hole, this last bar is a persistent one. These ones are small duration ones that can be ignored. But now we again increase, obviously there will not be any hole. That means the number of holes will be 0. Here you can see the corresponding to this value, there will not be any hole. Further increase. Therefore, if this is what is we are getting here. increasing the values, and the holes are gone. And finally, this is a better picturization. We have a D here, and construct balls with a radius D. And again, how to construct a complex there. You can see that the complex is constructed with this neighborhood relation using this. And again, if I decrease the radius, if I increase the radius, this again still I decrease the radius. You can see that now this is the filter here, filtration complex here. And if I again decrease it, you will get another one. But by varying, well, if you increase and very large, it will become a complete graph, and there will not be any hole, or completely filled graph you will be getting. Therefore, this is how we are getting. This is another example. This is how the barcodes are being constructed for the earlier given example. If you increase it, the barcode becomes like this. And if you very much increase, it is going like this. And this is the final example I have here. In fact, I told you that we don't even know from which dimension, these points are coming. Therefore, what you having, if I have a points like this, I have a point cloud here, and I told you that we will construct a barcode for each dimension. Dimension 0, x0, dimension 1 and dimension 2 we will construct. And when the, obviously here you can see that, and when the filtration parameter value is 0, obviously all are disconnected. And if it comes here, say this is the connectivity of, this is a figure there, then you can see that there are this much bars are here, that this you count the number of bars, that will give you in dimension 1, that will give you the number of connected components in this figure. Number of connected components. When you again increase the filtration parameter, this is a second filtered complex, this is the second filtered complex, and again you can see that there are this much 1 2 3 4 5 6 connected components will be there. And you can see that there are two things are there. You can see that in fact two holes are coming here. These two holes are coming here, 1 2. So there are two bars are cut with this particular value. Again you increase, again there is only one connected component, all are connected, only one component. Therefore, this persists in one dimension. This time persists in one dimension. That is all connected only one component. And you can see that 1, 2, 3, 3 are there. 3 are there. 1, 2, 3 holes are there. And there are no voids. Again, if you come over here, the numbers will be given. And given number 4, here you can see that there will be one void will be coming in between. That is, there is a in H2 dimension there will be one. And here also the numbers will be, here it is persistent in one dimension. This one is persistent in this one is persistent in 0 dimension. This is persistent in 1 dimension. This is persistent in dimension 2. Therefore, this is the direction in which the persistent parameter epsilon is increased. That means corresponding to each dimension, you will get a barcode. Corresponding to each dimension, you will get a barcode. I think I am audible now. There is some connectivity problem.
Yes, sir.
Hello?
Yes, sir.
Hello? Hello?
Yes, sir. Now it is audible.
Hello? Hello, sir. Hello? Hello?
Sir, any problem?
Hello? Hello? Hello, I am connecting from another device.
Sunil sir, you are not audible. It's,
I have connected from another device. Is it okay now?
yeah, okay.
In fact, there is some connectivity problem with the institute connection is here. Now I am connecting from another device, and I will maybe winding up maybe 10 minutes. And I hope that now it is okay. Okay. Yes.
Okay.
Okay, now you can see. No problem. And this is what is the final slide I have shown for the bar, how these things can be incorporated. Therefore, this is the barcode that we obtained, one for each dimension you will obtain. You will obtain one barcode for each dimension. And counting the number of holes. In fact, our holes or the analogous ones in other dimension can also be done here. Therefore, in H0, now you can see that for a particular value of for a particular value of the filtration parameter, you will get the bars here. This is a persistent over H0, and this is a persistent over H1, and this one is the persistent over H2. In that way, we can get an idea of what is the shape of the data. Now, how to interpret this barcode that I have already explained. The barcode starts when there is a birth of a particular hole or its analogous of the hole in other dimension happens. And at death, at the point of death, or that particular hole merges with an earlier existing ones, we stop that particular bar. Therefore, how that bars are being drawn, it is already mentioned I have. And 𝑉𝒐𝒐𝒏 numbers are also encoded in the barcode. I know I told you that at a particular value of epsilon, at a particular value of the filtration parameter epsilon, and you see you draw a vertical line on that and find out that line cuts with how many number of bars, and that will give you the 𝒏 number corresponding to that particular value of epsilon and the particular dimension P. I told you that each bar, there will be one bar for each dimension, and the number of points where that line cuts the bar, how many bars the line cuts in each dimension will give you the persistent 𝒏 number associated with So this is how this barcodes can be used for representing the feature of the data as well as finding the persistent Betty numbers. Betty numbers, how Betty numbers are also encoded in that. Now these are my references.
Hello, sir.
Yes.
Hello.
Hello.
Yeah, sir.
Hello.
Thank you for such a nice and informative talk.
Yeah.
And I have some questions
Thank
from this topic.
Yeah.
Actually, if I'm not wrong, this is a part of topological data size. Is it fine?
The TDA. It's a part of TDA, topological data analysis.
Yeah, it's a part of topological data analysis. Now, my question is that after knowing the Betti number, so what can we conclude about the data? Because if I consider in the sense of statistical analysis of data, so we can say that this is the result, so we can improve or we can do this precautions in case of data analysis. But from the knowing the Betti number and then calculation of it, so what we can conclude about the prediction or about the forecasting?
I am not an expert in statistics, but still I can say that you can get an idea of what is the shape of the data, or how that where the data, in fact, where the data are accumulated, and where there is a less frequency and more frequency. All these things can be observed by looking into the structure of the data. That means a whole means usually a whole happens only when there is a less what we say frequency of the data. Wherever the data are frequent, wherever the data are more clustered around, obviously there is a clustering will be there. For the clustering techniques, there is another application of this one, that this can be used, these barcodes can be used for clustering techniques. That is the application, I think.
Okay, so I also found some applications that Professor Gullar Carlson did some applications in medical science, and he has been consulting with medical practitioners also. So anyway, sir, if you don't mind, would you like to show the reference once more? Because I missed the reference, just reference section once more.
References.
Yeah, just a reference.
No problem. I can share the entire slides. No problem. I will send you the
But you can share just a reference, so it will be a little bit helpful for us. Already the topic is quite interesting.
I will share. No problem.
Any more questions? Teacher, sir?
Hello, sir.
Seems like there are no more questions, and we can conclude this program.
I think, sir. I think Sunil sir will share one more time the reference slide.
Reference slide ഒന്നുകൂടെ ഷെയർ ചെയ്യണോ? Okay.
Now, we are in the concluding session. Thank you, sir. We will think that no more questions now. Just a reminder, please be sure to type for getting participant certificate. Don't forget to submit the feedback form available in the chat box. I take this opportunity to thank our resource person. It is a great honor to propose vote of thanks to all who have helped in making this webinar a resounding success. First of all, I would like to propose a hearty vote of thanks to our chief guest, Dr. Jochen Joseph, principal of our college, who inaugurated the webinar series for gracing today's section. Thank you, sir, for your very interesting and thought-provoking address. Now, I would like to thank our distinguished speaker, Dr. Sunil Jacob John of NIT Calicut, for making an excellent presentation and making this webinar interesting and meaningful. The topics introduced here, including persistent homology, persistence barcode, simplicial homology, simplicial complex Betty numbers, and persistent Betty numbers, all are very helpful for research scholars, PG students, and all research aspirants. Thank you very much, Dr. Sunil Jacob John, sir. I would like to express our profound gratitude to our HOD, 𝒏𝒕𝒓𝒔𝒕𝒊𝒐𝒏 Joseph, IQAC coordinator Jubin Anthony, and the teachers of our department for their presence in this webinar. Finally, the wonderful students, research scholars, teachers, and participants from all over the country. I thank them for making this webinar a great success. Once again, I thank all for your cordial cooperation, and we will conclude today's section. And one announcement is there. The next webinar in this series, that is webinar 2, that is on 10th September, Thursday, afternoon 3 p.m. The topic is permutation group by Sri 𝒏𝒐𝒐𝒏𝒕𝒓𝒔𝒊𝒐𝒏, as Associate Professor, Government Women's College, Thiruvananthapuram. The today's section come to an end. Once again, thank the resource person and all the participants. Thank you all.
Thank you very much for all the nice words. In fact, this forms a part of topological data analysis. Whatever I have presented today is just a beginning of all those things. And there are from the messages I can see that there are many participants asking for the slides of today's presentation. In fact, I will send the slides with the organizers. There, please send it to all. I will share the slides in WhatsApp with the organizers and now itself, and they can make it available for all the participants. I think that will be okay. I am thankful to organizers, especially principal, head of the department, Jijo, and my friend Indulal, for giving me an opportunity and talking to you. In fact, I hope that it was effective and there was not much problem due to connectivity and other things. And I'm happy to share the slides, and the organizers, please forward the share to all. Thank you all. Thank you for your cooperation.